Hi, I'm Rebecca Downey. I teach 5th grade at Anderson Elementary, and the lesson you're about to see is a focus on higher order questioning as students work with operations and fractions. My class has 30% free or reduced lunch, 2 ESOL learners, 43% are gifted learners, and we have 1 active 504 plan. Our learning goals for this lesson are for students to solve open-ended problems working together by using visual models or writing equations. They should also be able to demonstrate mastery of computations with fractions and be able to critique mathematical reasoning of their own and others. This lesson falls in quadrant 4 of the BEST learning cycle as students independently work through tasks to show their mastery. The instructional strategies implemented in this lesson include open-ended questions that allow for more than one correct answer, student collaboration, use of manipulatives, student presentations, and critique cards in the use of exit slips. All problems used in the lesson were found in the book Good Questions for Math Teaching by Peter Sullivan and Pat Lilburn. I'm going to have you work with a partner, and I'm going to give you a problem. The problem is going to be challenging initially, right? That's okay. Our math practices need to make sense of problems and persevere in problem solving. So what I'm looking for today is initially you're going to be like, I gotta do what? I want to see that perseverance, all right? We also have that you have to reason abstractly and quantitatively. I want to see your number and fractions. What do I already know? How can I apply that? And how can I solve this problem? These are great questions, great problems, because there's more than one answer. Okay? So you're talking with your partner, and your partner might be going down a completely different path than you are, but you both might be correct. How are you going to work through that? What path are you going to choose? Ultimately, you're going to have to explain your reasoning to the rest of the class. The beautiful thing about this activity is you and your partner have one problem. Most likely, another partnership in the class has the same problem. My hope is that I'll see different solutions. Okay, so it's going to be very interesting to see how you work and then to compare. Okay, I'm going to give you poster paper. All right. When you have your poster paper, I think it would be a great idea to take your problem and to glue it to the back so we don't lose this. Right? Okay. All right. You're then going to need to rewrite the problem nice and large so you can see them and display them on one and the other side. You and your partner are going to work it out. You're going to solve. Can you use fraction kits to solve? Absolutely. Pull out your fraction kits if that helps you. Can you use pattern blocks to solve? Absolutely, if that helps you. Can you write computations? Get notebook paper? Make mistakes. Figure it out. Work backwards. Whatever you need to do. Draw a picture. Whatever strategies you have in your toolbox that will help you solve it, use those things. Don't throw it away. If you're showing me your thinking, I don't want you to throw it away. I want to see how you think. You and your partner might come up with different things. Discuss which one you want to choose. When you have solved the problem and you're confident in your solution, then you're going to take a second poster and you're going to go ahead and show us your solution. You're going to go ahead and document and record your solution. You can write the equation, you can draw pictures, fractions, whatever you need to do on this piece of paper, because ultimately you're going to present your problem and your solution to the class. Right? Lots of information just came at you. Questions to clarify.
Okay, our problem was the difference of two fractions with different denominators is 3/16. What might those two fractions be? Okay, so I knew 5 minus 2 equals 3, so 5/16 minus 3/16 equals 3/16. And we're going to simplify our numbers, get a different denominator, so simplify it to 1/8. And since 1/8 is equal to 2/16, it's the same, so it would have the same difference, and they have different denominators like the problem set.
Outstanding. Very good. I like the way you guys work together and you kind of bounce off. I love how you started out with that 5, take away 2 is 3. So what I know about whole numbers, I can go ahead and apply to what I know about fractions. Outstanding work. So your question is, what 3 fractions with different denominators might I add together to get a sum of 1/2? So you're asking if you can do 2/6, 1/12, and 2/24.
1/2 is 2/6, it's 2 pieces.
All right, so I see that you have 3 add-ins. I'm going to come in so I can kind of understand a little bit more what you've done. All right, I see that you have 2/6. Explain what you have on your paper here for me.
Okay, 2/6 is equal to 4/12. 2/24 is equal to 1/12. So 4/12 plus 1/12 plus 1/12, since 2/24 is equal to 1/12. I got 6/16.
You got 6/16.
6/12.
Oh.
6/12 to 1 equals 1/2. I accidentally put 16 there.
That's no problem, but you were able to revise, you found your own mistake, which is good. Error analysis is good. So go ahead and correct your mistake. So let me understand what you've said. Actually, instead of having me repeat it, Sophia, can you repeat what his thinking is? Do you think he's got a solution?
I think it was correct. I wasn't sure if it was like only 3 fractions, because it'd be 2/24, so like if that would count as 3 fractions.
All right, so let me make sure I understand your question. So you have 2/6 as your first addend, you have 1/12 as your second addend, and you have 2/24 as your third addend. Why are you confused? I don't think I'm understanding.
Because there's 2/6, so when we put it on there, it has 2 pieces. 1/12 is 1 piece, and then there's 5 pieces because there's 2/24.
All right, I think I understand now. What you've done is you've used the fraction pieces, the manipulatives, to help you come up with this solution. But when you do 2/6, you're actually using 2 pieces. But those 2 pieces represent 1 fraction. Does that answer your question now? Excellent. You guys have been very patient with me as I work through understanding what your question was. I think you've done fabulous because you have the 3 addends, they're fractions. Okay, Aiden and Anna, explain to me what your problem is and what your reasoning is.
Our problem is a rectangle has a parameter of 2 units. Write the equations, demonstrate visual models, and be prepared to explain your thinking and justify your reasoning to the class.
Okay, good. So that's your problem. Now I see, Anna, that you got busy right away. So what did you do here?
We thought that since you needed 2 units for the whole entire perimeter of the rectangle, you would have to split that in half. But then 1/2, 1/2, 1/2, 1/2, that would be a square. Remembered that a square is also the same thing as a rectangle.
Excellent. Good reasoning.
So the next thing we did was we multiplied 1/2 times 1/2, which got us 1/4. And he also multiplied 5/10 times 5/10 to make it a little easier, and we got like 25 hundredths.
Excellent. So what made you do 5/10 times 5/10 to get 25 hundredths?
Well, I knew half was 5/10 as a decimal, so I just multiplied it.
Perfect, perfect. Maya said that we're confused. So explain to me what you're doing right over here now, Selma, to ease up on the confusion.
Well, I did decimals, and I have 2, and then like I subtracted decimals from it to get to find out what like if I could find out the sides of the rectangle.
All right, so I like your strategy. So she started with 2 and she's working backwards, but you're using decimals, which I have no problem with. So now that she's got possible values, what are you going to have to do, because you have them in decimals? What do you have to do now, Leonard?
You make them in fractions.
Yeah, I've been like doing random problems to try and figure out like what equals a whole, because I know like they can't be the same fractions, only like the width can be the same and the lengths can be the same.
Good. All right, so you were implementing a guess and check strategy, and Selma implemented a work backwards strategy. So
At first, I got kind of confused on what we were supposed to do. Then I found out like we had to find out the perimeter first to find out the area. So we used 1/2 as all of them, because then that would be a square. Then we remembered that a square is the same thing as a rectangle.
as students made the presentations to the class, their peers critiqued the mathematical reasoning of their solutions. Our class has used talk moves as a tool to promote math discussion. When Anna and Aiden solved their problem by saying a square can be a rectangle, this challenged some of my students' reasoning, as can be seen in their critique cards. The high-level thinking in my classroom has allowed students to generate their own questions. I plan to take these critique cards and develop a new lesson where students must prove a square can be a rectangle. High-level thinking and higher-order questioning occurs when you plan lessons that allow students to think critically and then listening as they begin to question for their own understanding.